Welcome back to ESS 182, Chapter 6, Lecture 2. We are going on to looking at minerals and rocks today. Last time we really focused on the Earth, the large geological processes of the tectonic plates, things like that. Now we'll be talking about the rock cycle. So I brought back the Chapter 6 key ideas. Number 3 is really where this lecture is focusing on. Number 4 and 5 will be the last two sections we'll talk about in the next PowerPoint. So we want to describe the rock cycle and discuss its importance in environmental science. So what the rock cycle is how minerals and elements kind of move through the earth, up and down through the magma and back across the earth. It's a very slow process, but it's how all these rocks get recycled throughout our earth. So it's this constant formation and destruction of rocks. It's very slow, slowest of all the cycles, even though we can think of something like the water and nitrogen cycle as seemingly pretty slow. This one is very slow. So what we mean by rock is the lithosphere. So that layer on top of the earth is made up of all these types of minerals. So that rock layer is made up of large variations of minerals. And these minerals can be of compounds, so something like iron oxide, or they can be pure elements, silver and gold, mostly compounds. And they have some sort of uniform structure, usually crystalline structures, and they're a combination of all different types of elements. Not all, but many different types of elements. So that's what we mean by minerals. Here are examples from the book of just a few minerals. We're going to see some more later on too. The first is iron 2. Actually, this would be iron 4 sulfide. This is what's called fool's gold, pyrite. Looks very much like gold, but the density is quite a bit different. Graphite, this is a allotrope carbon, so a different type of pure carbon. And then on the right, we have halite, or table salt, sodium chloride, just a really beautiful large crystal of table salt. So those are examples of what we mean by minerals. So what is the rock cycle? Well, this might look a little bit complicated, but it's not too complicated when you start here down at the magma. So all these rocks that we see, and there's going to be three main kinds: igneous, metamorphic, and sedimentary rock. They all come from magma. So magma is this hot mixture, and it gets up into the lithosphere and up to the surface and forms these large rock and mineral deposits. So we've got this cycle of magma coming up to the surface, and then weathering and erosion start breaking this apart. That's then transported by the wind through other physical means around the world through this weathering and erosion process. Glaciers can be pushing it along, and eventually it is compressed down to different layers again. Some of those become sedimentary layers. Some of these are metamorphic rocks that get pressed by really high pressures. But these get pressed down and down and down. Eventually, they get low enough through subduction. So you have the tectonic plates pushing them back underneath other plates into the magma again, where they get melted down. And then slowly but surely, they get pushed back up, and this process occurs again. So the igneous, metamorphic, and sedimentary are just three types of rocks that can form from the magma. But this is the general cycle. So go ahead and hit pause and eventually get to know these different terms and different cycles for the rock cycle. So let's talk about all these three rocks. So I noticed there's igneous, metamorphic, and sedimentary rock, the three rocks that come from magma. Igneous is the first one we'll talk about here, and they're all from magma, but they form in different ways. Igneous are the ones that directly come from magma. So they're the most, it's I guess the easiest to form, I suppose, but they're classified as either basalt types, basaltic, or granite types. We're going to look at some of these as well. Sedimentary rocks are things like mud or sands, gravels. These can compress down and they can make these kind of layers, these sedimentary style layers. Metamorphic, on the other hand, these can be igneous or sedimentary or other metamorphic rocks, any of these types together, and they're subjected to really high temperatures and pressures to get drastically different kinds of rocks. So those are the three that we see. Igneous are directly from, sedimentary come from layers compressed, metamorphic come from really high pressure and high temperatures. So let's look at some of these igneous rocks. And this, I believe this looks like a granite surface. And we'll see some more of these in a second. So here's some, oh, I'm sorry. I guess we're starting with, let's start with igneous. We'll go back to that sedimentary screen. So let's look at some igneous rocks first, directly from the magma. So I pulled some of these from the internet from geology.com. Granite versus basaltic. Notice these are like the two kind of basic forms. The broad classification are basaltic versus granitic rocks. Basaltic are a lot darker. They have different elements to give them that color, and granitic are much lighter. But this is the pure forms, what we call basalt and granite. So this is basalt, this is granite. You think of granite tabletops. Granite is an igneous rock. It comes directly from magma. Obsidian is another type of rock. And then pumice. Pumice, you might have seen pumice stones or pumice, these pumice rocks that you can buy for body cleansing. This is really, really light and not very dense kind of rock. So really, the only difference between these is basically the cooling process. Was there gas around when it cooled? So the magma is going to come out and cool down and form these different types of minerals in different ways. Straight from magma, but then different elements, different concentrations of elements get into these. They form in different slow or quick processes. Some have more pressure than others. Pumice has a lot of gas bubbles inside it as it cools, so there's a lot of air pockets inside here. So it really just comes down to how these form. And I'm no expert on this. If you went to geology.com, though, it can tell you a lot more about each one of these type of igneous rocks. So that's the first one, rocks that form directly from the magma source. Again, basaltic are darker, granitic rocks. Classifications are a lot lighter in their color. So next is sedimentary rocks. I pulled a few of these, some ones that you're familiar with most likely. First of all, coal. This is a type of sedimentary rock, actually. It takes a decent amount of pressure to create coal, but it's a lot of carbon inside here. Iron ore. Iron is actually a type of sedimentary rock. Limestone and sandstone. Limestone is used for a lot of sculptures or a lot of buildings. It wouldn't be a great building material, though, in terms of acid rain. Acid rain can actually decompose this. So all of these kind of terms you might have heard before, sandstone, limestone, granite, they're all specific types of rock that all come from magma, but they're formed in different ways. So again, the difference between these are the different elemental compositions and the amount of time or the amount of just different processes how they're formed. Again, I'm not a geological expert. I couldn't look at a rock and tell you how it was formed. You would have to learn a lot about that, but I like looking at these different types of rocks, identifying them by the classification. Lastly, we've got the metamorphic kinds. These take a lot of pressure and energy to make. So you're taking an igneous rock, or maybe you're taking a sedimentary rock, or maybe you even already have a metamorphic rock, and that rock is also subjected to high temperatures, pressures. You form these new rocks called metamorphic rocks. And the pressures that form these rocks, they can make profound physical and chemical changes. So really interesting changes. And I pulled some of these. This is from the book. It says they include things like slate, marble, and anthracite. So like a marble countertop or a marble building, marble is a type of metamorphic rock. Here's a compound example of slate. This is lapis lazuli, and it's not a gemstone like maybe I kind of thought it might be. If you have a nice polished bead of it, it's actually a metamorphic rock. Really beautiful blue colored rock. Very rare to see this type of color in one of these rock styles. Thinking about all these kinds, it makes me want to, I don't know, I want to learn more about this now, actually reading this chapter, because I love going out to the rivers and picking up rocks and looking at them, see what style they are. It'd be fun to start identifying some of them and saying, oh, that's a sedimentary rock or that's an igneous rock, and then seeing what types I could find out there. Because there's just a lot of different types of these minerals out there. The last one in the middle is anthracite. I'm a big Office fan, so I remember anthracite from the Anthracite Museum in Scranton, Pennsylvania. So this is a form of coal, but it's subjected to a lot higher pressure. And yeah, any Office fans out there? The Anthracite Heritage Museum. So anthracite is a type of metamorphic rock, a type of coal, high carbon content. Okay, so that's the type of rocks here. Let's go back to the beginning. So describe the rock cycle. That's what we're doing, the rock cycle and types of rocks within that key idea. And then discuss its importance in environmental science. That's what a little bit of the back end is going to be about. So in environmental science, we study these type of rocks, and we study how they are transported and how they weathered. So what happens when you leave these rocks out into the elements? They're exposed to air, water, or chemicals, sometimes biological agents. they can start degrading the rocks. The one on the left, this is water that comes into these cracks, freezes during the winter, and expands. As water freezes, it gets less dense and has higher volume. So it actually expands and you can form cracks. I mean, this is what happens to our asphalt surfaces every year in really hot in really cold climates. Or you might have a physical biological agent. So these roots can come start clawing their way into the cracks and weathering and breaking apart these rocks. So that's physical weathering. So weathering means you are actually exposing them to the elements and degrading and breaking them down. That's what weathering really is. Oh yes, that's right. Chemical weathering. This is interesting too. So here we have some really beautiful caves. These are a lot of limestone in these caves, and limestone is reactive to weak or strong acids. So water that has a lot of carbon dioxide dissolved in it produces a decent amount of carbonic acid inside that water. And that can come in and start weathering these as water starts to drip down. Slowly but surely, it starts to dissolve these rocks and form these kind of patterns. So this is what we mean by chemical weathering. In this case, we have a acid as our chemical doing the weathering. Erosion, on the other hand, this means physical removal of rock fragments from a landscape or ecosystem. So this is really weathering, breaking apart, degrading the rocks. But notice all the rock is pretty much still here. It's just been degraded. Chemical weathering, the rocks are still here. They've just been kind of shaved down a little bit. Erosion, on the other hand, think of actual rocks being kind of moved around. Physical removal. So wind coming along and just pushing and scraping rocks away. Water pushing and scraping rocks away from where it used to be. Ice, so a big glacier coming in and moving chunks of rocks across the landscape. And even living organisms can erode materials. So if you have something burrowing underneath a hill and then that thing collapses eventually and the rocks tumble down. So that's erosion is kind of moving the material away. Humans can cause substantial erosion issues. You see this a lot too on near rivers. So if they're moving a lot of soil from the sides of rivers to use for other projects, the sides of the river can start to collapse and you get this physical erosion of the sides of rivers. Here's a beautiful example of erosion. This is the Badlands of South Dakota. And this, I mean, a lot of different ways this could have happened. Water coming through, pushing along the sides, glaciers, wind. This is the result of really softer type of rocks. So you got these erosion of sedimentary rock types, shales and clays. So these are less resistant to erosion. So over time, they erode much easier and you get these really beautiful patterns. So the Badlands are a pretty cool example of natural erosion. So deposition, so what actually happens to that material? So erosion is a process of moving the material. Deposition is the actual accumulation or depositing of that material. It's got to go somewhere, right? So after the accumulation process, let's say even you have like a whole bunch of prairie dogs or something. They're burrowing under the soil, they're causing erosion, but then the soil has to go somewhere. So they're either putting it on top or they're physically moving it somewhere else. So deposition is how we actually move the material. If you think of a man-made erosion process, maybe we're mining and pulling out tons of earth from somewhere. If we're doing a bunch of eroding, then we have to actually move it somewhere. We've got to place it into piles somewhere. We have to use it for something. So that's where the deposition comes from. It has to go somewhere. So too much unnatural deposition can be bad for specific environments, depending on how we do that. So that is our kind of quick jaunt for this section. I only wanted to go through just one of these key ideas here because I wanted to kind of I wanted to divide the rock cycle from the soil formation. So next time we will finish up the chapter and we were going to study the last pieces of the puzzle of the soil formation and what in the world is inside soil and how does it form, things like that. So I will see you guys next time for the last pieces of chapter 6.